Every heartbeat you feel right now is energy. Every thought firing in your brain, every star burning in the sky. Energy runs all of it. But here is the thing. Nobody knows what energy actually is. One of the greatest physicists who ever lived, Richard Feynman, stood in front of a room full of scientists and said exactly that, out loud, in public. No answer. We will trace energy from the food in your stomach to the edge of the universe. From a lightning bolt hotter than the sun's surface to the invisible force pulling galaxies apart right now. If you enjoy the journey, like and subscribe. It genuinely helps. Now, prepare yourself. We begin. Pick up your hand and drop it on your knee. That thud, that movement, that tiny jolt of heat where skin hits skin, all of it was energy. Every single piece of that moment. Now try to grab the energy itself. Squeeze it. Hold it up to the light. You cannot. Your hand passes right through the idea like it was never there. That is the strangest thing about energy. It is everywhere. It powers every star in the sky, every heartbeat in your chest, every thought firing right now behind your eyes. And yet, if someone asks you to point to it, you are stuck. You can point to a fire. You can point to a running engine. But the energy inside those things? Invisible, untouchable, completely beyond reach. Most people assume that scientists figured this out a long time ago. They assume energy is just a textbook word for heat, or light, or electricity. Something boring and solved. But crack open a university-level physics textbook and look at how it defines energy. It says, energy is the ability to do work. Then look up work. It says, work is done when energy is transferred. The definition of energy uses the word work. The definition of work uses the word energy. The whole thing loops back on itself, and at no point does anyone ever say what energy actually is. This has been true for centuries. Scientists can measure energy with stunning precision. They can track it as it moves from a burning log to a spinning turbine to a glowing light bulb. They can calculate exactly how much of it exists in a single grain of rice. They can predict how it will behave 1 billion years from now with equations so accurate they have never once been wrong. And yet, after all of that, the thing itself, the actual substance or property or force that all those equations describe, remains completely unknown. Think about what that means. Humanity has built nuclear reactors, launched probes to the edge of the solar system, and decoded the human genome. All of it ran on energy. All of it depended on energy behaving in predictable ways. And the entire time, no scientist on Earth could tell you what that energy fundamentally was. Here is a comparison that might help land the scale of this mystery. Imagine you hire a chef who cooks the most incredible meals you have ever tasted. Perfect. Every single time. Then, one day you ask the chef, what are these meals actually made of? And the chef smiles and says, I have no idea. I just follow the recipe. That is physics and energy. The recipe works perfectly. The ingredients remain a mystery. What scientists do know is this: energy shows up in different forms. Heat, light, motion, chemical bonds, sound, electricity, gravity, every single one of those looks different, feels different, and behaves differently. But they all convert into each other without losing anything. A fire heats water. Water pressure spins a turbine. The turbine generates electricity. The electricity charges your phone. Each step looks totally different. The total energy stays exactly the same. That pattern, energy changing shape but never disappearing, is one of the most rock-solid rules in all of science. No experiment has ever broken it. No machine has ever cheated it. But what happens when you follow energy all the way back to where it started? That is where things get genuinely strange. You eat a burger. 20 minutes later you are running down the street. Something happened in between. Something turned ground beef and a bun into moving legs and a pounding heart. That process is one of the most remarkable chains in all of biology, and most people have no idea how it actually works. Start with the burger itself. Inside every bite sits a tightly packed structure of molecules, proteins, fats, carbohydrates. Each one holds energy locked up inside chemical bonds, the invisible connections between atoms. Those bonds store energy the same way a compressed spring stores energy. Tight, ready, waiting to release. When your stomach breaks that food apart and your cells absorb it, tiny molecular machines inside your body begin cracking those bonds open. The energy releases. Your cells capture it and use it to build something called adenosine triphosphate. Most people have heard the abbreviation, but the full name matters here. Adenosine triphosphate is basically a rechargeable battery the size of a molecule, and your body makes millions of them every second. When a muscle cell needs to move, it burns one of those tiny batteries. The battery releases its stored energy. The muscle fiber contracts. Millions of fibers contracting at once move your leg forward. One stride, then another. So the energy travelled from the sun, into the grass, into the cow that ate the grass, into the burger, into your stomach, into your cells, into those molecular batteries, into your muscles, and finally into the motion of your running body. Every single link in that chain is real. Every conversion follows the same accounting rules. Nothing got created along the way. Nothing disappeared. The energy just kept changing shape. And here is where it gets interesting. Every one of those conversions is imperfect. Your muscle does not turn all that food energy into motion. A large chunk of it becomes body heat instead. That is why you sweat when you run. Your body is basically a furnace that also happens to move. The motion is almost a side effect of all the heat being generated. Scientists measure this in terms of efficiency. A car engine converts roughly 20 to 30% of its fuel into actual motion. The rest becomes heat that bleeds out through the exhaust and the radiator. Your muscles do about the same. All that energy from the burger, and only a fraction of it actually moves you. The rest warms you up. Now flip that image around. Every warm-blooded creature on Earth is bleeding energy as heat constantly. Every second of every day, your body radiates heat into the air around it. You are, in a very real physical sense, a slow-burning candle. The energy that burned in the sun a few years ago is now leaving your skin as warmth. That chain from sunlight to food to motion to heat plays out trillions of times a day across every living thing on the planet. And none of it creates or destroys a single unit of energy. It only moves it forward. But the real puzzle is not where the energy goes. The real puzzle is what it was in the first place before any of that started. The man who got closest to that question walked into a lecture hall and handed the audience something they were not expecting. An honest answer. It was 1961. Richard Feynman stood in front of a classroom at the California Institute of Technology, one of the most competitive science universities in the world. Feynman was already legendary. He had worked on the atomic bomb project as a young man. He had won the Nobel Prize in Physics for work that redefined how scientists think about light and matter. He was famous for being able to explain impossible things in simple words. Students lined up to get into his lectures. That day, he was giving a lecture on energy. He started with the basics, built up the ideas, walked the room through everything physics had discovered over 3 centuries of work. And then he stopped. He looked at the room and said something that changed how a lot of scientists thought about their own field. He said that in physics, we have no knowledge of what energy is. He did not say it as a failure, he said it as a fact, a boundary condition. Here is everything we know how to do with energy. Here are all the rules it follows. Here are the equations that predict its behaviour with perfect accuracy. And here, at the centre of all of it, is a blank space where the answer to the most basic question should be. What is energy? Nobody knows. That statement from one of the sharpest minds in the history of science has never been corrected. 60 years of physics research since that lecture, including quantum computers and gravitational wave detectors and experiments that cost billions of dollars, And the answer to that core question is still the same blank space Feynman pointed to. What makes this even stranger is that Feynman was not describing a gap scientists expected to fill soon. He was describing something that may be fundamentally unfillable. Energy might be the kind of thing that cannot be explained in more basic terms because it is already one of the most basic things there is. Think of it this way. If someone asks you why fire is hot, you can say the atoms inside it are moving fast. If they ask why fast-moving atoms feel hot, you can explain how they bump into your skin and transfer their motion. Each question has a deeper answer, and you keep going. But at some point, you hit a flaw, a thing that just is and cannot be broken down further. Energy might be that flaw. Scientists can describe how it moves. They can write equations for how it transforms from one form to another. They can predict with complete accuracy how much of it will be in any system at any future point in time. But the thing itself, the reason the number stays constant, the reason this property exists at all, that remains completely open. And here is where it gets genuinely uncomfortable. The equations that describe energy are some of the most tested, most verified, most battle-hardened ideas in all of science. They work every time, without a single exception, across every scale from subatomic particles to galaxy clusters. The fact that those equations describe something we cannot fundamentally define suggests that maybe our idea of understanding has limits. Feynman thought so. He believed that physics was the discipline of knowing how, not always knowing why. But one person got closer to the why than almost anyone else, and that person was almost lost to history entirely for reasons that had nothing to do with the quality of her work. Open any high school physics textbook, turn to the chapter on energy, read the definition out loud. Energy is the ability to do work. Now look up work in the same book. Work is the transfer of energy from one object to another. Read both of those again. Slowly, energy is defined using work. Work is defined using energy. The two terms point at each other like two people in a circle. Each one claiming the other is the real answer. Neither one ever lands on solid ground. This is called a circular definition, and in most subjects, finding a circular definition is a sign that someone got lazy with the writing. But in physics, this particular circle has survived every attempt to escape it for over 300 years. Smart people have tried, really smart people, and the circle remains. It is not that physicists are bad at defining things, they are extraordinary at it. Ask a physicist to define the charge of an electron, and you will get a precise, layered answer that connects to dozens of measurable quantities. Ask for a definition of the speed of light, and you will get a number accurate to 12 decimal places. Ask what a quark is, and you will get a description in terms of mass, spin and force interactions that can be tested and verified. Ask what energy is, and eventually, after enough layers, you end up back at the same circle. Some physicists argue this is actually fine. They say energy is a mathematical quantity, a number that systems carry, and asking what it is made of is like asking what the number 7 is made of. 7 is not made of anything. It is a concept, a measurement, a relationship between things. And maybe energy is the same. That argument has real support. But it also raises an uncomfortable question. If energy is just a number, just a mathematical property of the universe, then what is the universe actually made of? Because when you follow every particle, every field, every force, all the way down to its deepest description, you end up with equations, relationships between quantities, numbers. At some point you have to ask, is there anything underneath the math? Or is the math all there is? Physicists call this the interpretation problem. The equations describe reality so well that we trust them completely. But the equations are abstract. They do not tell us what is actually happening in physical space. They just tell us what measurements will say. Here is a comparison. Imagine you get a perfect map of a city. Every street, every building, every elevation. The map is 100% accurate. You can use it to navigate anywhere. but the map is still just lines and symbols. At no point does the map tell you what the city actually feels like to stand in. The equations of energy are like a perfect map of something we have never actually stood inside. And here is what makes this worse. The definitions we do have are recent. For most of human history, nobody had the word energy at all in a scientific sense. The concept that heat, motion, and light are all versions of the same underlying thing was an idea that took centuries to piece together. The woman who finally gave that concept a mathematical foundation was working in a world that did everything it could to push her out. And what she discovered connected energy to something far stranger than anyone expected. Picture the world's most obsessive accountant. Every morning, this accountant counts every single unit of energy in the universe, every photon travelling between galaxies, every vibrating atom in every rock on every planet, every heartbeat of every living thing, and every single morning, the total is the same number it was the day before. The accountant never finds a surplus, never finds a shortage. The books always balance. Perfectly. That is conservation of energy. And for centuries, it looked like a law that the universe was obeying, a rule imposed from outside, like a speed limit painted on a cosmic highway. Scientists knew the rule held, they could measure it holding, but none of them could explain why. Then, in 1918, a mathematician named Emmy Noether did something extraordinary. She proved that conservation of energy is not a rule the universe follows. It is a consequence of something much deeper, something about the structure of time itself. Her proof goes like this. The laws of physics today are the same as the laws of physics yesterday. Drop a ball on a Tuesday, it falls at the same rate as a ball you drop on a Thursday. Burn a candle in ancient Rome, the chemical reactions follow the same rules as burning a candle tonight. The laws do not change as time passes. Noether proved mathematically that any system whose laws do not change over time will automatically conserve energy. The two things are locked together. Time symmetry produces energy conservation, the same way a shadow is produced by a solid object. One implies the other. Always, this is called Noether's theorem, and physicists consider it one of the most beautiful results in the history of science. It takes a mysterious rule and shows it as a natural outcome of a deeper structure. Energy is conserved because the universe is consistent across time. The laws tomorrow are the same as the laws today. And as long as that is true, energy stays constant. But here is what makes this idea dangerous to sit with too long. Noether's theorem also implies that if the laws of physics ever changed over time, energy conservation would break. If the fundamental rules of reality shifted, even slightly, energy would stop balancing. It would be created or destroyed. Do the laws of physics actually stay constant across all of time, for every moment since the Big Bang? Across the full lifespan of the universe until the last star burns out? Scientists strongly believe they do. Every measurement ever taken supports that belief. But belief and proof are different things. Nobody has measured the laws of physics in the first moments after the Big Bang. Nobody has measured them at the far edge of an accelerating universe where everything is stretching apart. The assumption that the laws are perfectly constant everywhere and always is an assumption. And now for the part that turns this from beautiful to strange. The cosmic accounting system, this perfect ledger of energy that never loses a single entry, has no physical location. You cannot open a vault somewhere and find energy stored. It lives entirely in the relationships between things, in the motion of particles, in the tension of fields, in the structure of space itself. Energy as a concept has no address, no substance, and the only reason it stays constant is because time keeps flowing forward the same way it always has, which raises a question so strange it is hard to even phrase properly. What happens to energy at the very edge of the universe, where space is stretching faster than light and time itself behaves differently? Hold a paperclip between your fingers. A standard metal paperclip weighs about 1 gram. That is roughly the same as a single dollar bill. Small, ordinary, completely forgettable. Inside that paperclip sits enough energy to power the city of New York for several hours. That statement is not an exaggeration. It follows directly from Einstein's equation, the most famous equation in science. Energy equals mass times the speed of light squared. Every gram of matter, any matter, holds an almost unimaginable amount of stored energy inside the bonds between its atoms and the mass of those atoms themselves. The speed of light is 186,000 miles per second. Square that number and you get something so large it barely fits in the human imagination. Multiply even a tiny mass by that squared value and the result is staggering. The problem is access. Unlocking that energy requires something physics has never fully achieved, a way to convert matter directly and completely into energy. The closest humanity has gotten is nuclear fission, which is what powers nuclear reactors and atomic bombs. But even that process only converts a tiny fraction of the total available mass into energy. The bombs dropped in World War II converted roughly 1% of their nuclear material into energy. 1%. And they leveled cities. A complete conversion, called matter-antimatter annihilation, converts 100% of mass into energy. But producing antimatter in large quantities requires enormous amounts of energy to begin with, and storing it without it touching regular matter is practically impossible with current technology. So the paperclip remains fully armed and entirely locked. Einstein published the equation in 1905. He was 26 years old. He was working as a clerk at a patent office in Switzerland because universities at the time did not take him seriously enough to offer him a research position. He submitted his findings to a physics journal during his spare time. The paper changed everything. It meant that mass and energy were the same thing, expressed differently. A solid object sitting still on a table is, in the deepest physical sense, a massive concentration of energy that has temporarily taken the form of matter. The table, the floor under it, the atoms in the air around it, all of it is energy in a different costume. When matter gets converted to energy, the costume comes off. The result is light, heat, radiation, movement. The total energy released equals exactly what Einstein's equation predicts. Every time. Without fail. This also runs in reverse. Energy can become matter. In the first moments after the Big Bang, the universe was so hot and so dense that pure energy was constantly converting into matter and back again. The particles that make up your body were born out of raw energy in that first fraction of a second. So here is the uncomfortable position that physics puts you in. Your own body contains more stored energy than a large collection of nuclear weapons. That energy is real, measurable, perfectly accounted for, and completely inaccessible, held in place by the same forces that hold atoms together. The paperclip on your desk is, in one very real sense, a bomb that will never go off. But the laws that keep it locked? Those laws have a story behind them too. A story discovered by a woman who should have been a household name, and almost was not. In 1918, the University of Göttingen in Germany had a problem. Emmy Noether was the most talented mathematician working there. Everyone knew it. The senior professors knew it. Her colleagues knew it. Noether herself knew it. But she was a woman, and at that time women were legally barred from receiving full academic positions at German universities. She worked for years without pay, giving lectures listed under a male colleague's name, doing the work while someone else got the credit. The mathematics she produced during that period would eventually be called some of the most important results of the 20th century. Her most famous proof, published in 1918, connected two things that seemed completely unrelated: the symmetries of the laws of physics and conservation laws. A conservation law is any rule that says a quantity stays constant. Energy is constant. Momentum is constant. Electric charge is constant. These rules had been observed and verified for centuries, but nobody had explained why they held. Noether did. She proved that every conservation law in physics corresponds exactly to a symmetry in the laws of nature, and the symmetry that produces energy conservation is time symmetry, the fact that the laws of physics are the same today as they were yesterday and will be the same tomorrow. Here is what that means in plain terms. Imagine you run a physics experiment on a Monday. You get a result. You run the same experiment on a Friday. You get the same result. The laws did not change between those 2 days. That consistency, that sameness across time, is what automatically guarantees that energy stays constant. Know the proof the connection is exact. Unbreakable. If the laws of physics are perfectly consistent across time, energy conservation is mathematically certain. If the laws shifted even slightly, energy conservation would fail. It would start leaking. Energy would appear from nowhere or vanish into nothing. The two things, time consistency and energy conservation, are not two separate facts. They are the same fact written in two different ways. When physicists finally understood the full depth of her work, they were stunned. Albert Einstein called her the most significant creative mathematical genius so far produced. That is not a minor compliment from a minor source. But Noether's theorem also opened a door that made physicists uneasy. If energy conservation depends on the laws of physics staying constant over time, what happens at the very edges of the universe where space is stretching at accelerating speeds? What happens inside a black hole where time itself bends and warps? Do the conservation laws still hold in places where time does not behave normally? The answer, according to most physicists, is that energy conservation becomes complicated in those extreme environments. The nice clean accounting system starts to bend at the edges of reality. Noether was eventually forced to flee Germany in 1933 when the ruling government began dismissing Jewish academics from their positions. She moved to the United States, took a position at a small college in Pennsylvania, and died just 2 years later from complications after surgery. She never received a major prize. Her name never became famous outside mathematics and physics. But the theorem she proved sits at the absolute foundation of modern physics, invisible and essential, the way foundations usually are. What she revealed is that energy conservation is not just a rule, it is a mirror of time. And time, as it turns out, has some extraordinary properties of its own. Imagine time just stops. Every particle in the universe freezes. Light stops mid-travel. Your heartbeat locks in place. The rotation of the Earth pauses. Every vibration, every wave, every motion in the entire universe halts simultaneously. According to Emmy Noether's theorem, in that frozen universe, energy conservation would cease to mean anything. Noether's proof depends on time flowing forward, on the laws of physics staying the same from one moment to the next. If there are no moments, if time does not pass, the entire mathematical structure that guarantees energy stays constant has nothing to operate on. But here is the part that gets stranger. A frozen universe is not really a thought experiment anymore. In the moments directly after the Big Bang, time itself was something different than it is today. The conditions were so extreme, the density so impossible, that the normal rules of space and time had not yet settled into the forms we know. Physicists describe this early period using terms like quantum gravity, meaning the point where quantum mechanics and the theory of general relativity both apply, and currently neither theory knows how to handle the other. In that early soup of everything, energy itself may not have been a fixed, conserved quantity. The universe may have started in a state where energy was not something that needed to add up. And as time expanded and cooled and stretched into something recognizable, energy conservation emerged as a property of the system, the way ice crystals emerge when water gets cold enough. This is not a settled idea in physics. It sits at the frontier where theory starts and certainty stops, but it is taken seriously by serious people, and it points at something deeply uncomfortable. The rule that energy is always conserved, the rule that everything in your life depends on without you ever thinking about it, may have an expiration date. Or more precisely, it may have had a beginning, a moment before which energy conservation did not exist as a law. If energy conservation could begin, it can end. Most physicists think this is extremely unlikely on any timeline shorter than the full lifespan of the universe, multiplied by numbers that lose meaning in human terms. The laws of physics appear rock solid and permanent to every instrument ever built. There is no evidence of any cracks. But Noether's theorem tells you what to watch for. If you ever measure energy in a closed system and find a discrepancy, something extra appearing from nowhere, or something vanishing without a trace, you are not looking at a measurement error. You are looking at a change in the laws of physics. You are watching time itself behave differently than it did yesterday. That has never happened in any experiment ever recorded. The books always balance. And yet the fact that the rule has a logical underpinning, a reason it holds, also means it has a condition under which it would not hold. That condition is a universe where time loses its consistency. Scientists have no evidence that is happening, but there is one place in the universe where time does something so extreme that nobody fully understands the consequences. A place where time may slow to a standstill from certain perspectives. A place where energy itself becomes impossible to track. That place is coming. But first, the object that moves faster than anything else and carries energy without having any mass at all. Stand outside on a clear day and feel the sun on your face. That warmth travelled 93 million miles to reach you. It left the surface of the sun about 8 minutes ago, moving at 186,000 miles per second. By the time it touches your skin, it has crossed an emptiness so large that most numbers fail to describe it. Now hold this in your head. The total energy the sun releases in a single second, across all directions, in every form, heat and light and radiation and charged particles, could power the entire human civilization for 500,000 years. 500,000 years. From before our species existed through everything we have ever built, through every future we can imagine, and far, far beyond it. All from 1 second. The sun does this every second, around the clock, and it has been doing it for about 4.5 billion years. It will continue for roughly another 5 billion years before it begins to run out of fuel. Where does all that energy come from? At the core of the sun, gravity squeezes hydrogen atoms so hard that their nuclei collide and fuse together, forming helium. The fused helium atom weighs slightly less than the 2 hydrogen atoms that created it. That missing mass converts directly into energy following Einstein's equation. A tiny difference in mass becomes a staggering release of radiation. Every second, the sun converts roughly 4 million tons of its own mass into pure energy. 4 million tons. That is more weight than every skyscraper in New York City combined, converted into light and heat every single second. And here is the part that makes this hard to sit with. All of that energy begins as gamma rays deep inside the sun's core. From there, it takes the energy roughly 100,000 years to fight its way from the core to the surface through a dense tangle of hot plasma. Each gamma ray gets absorbed and re-emitted millions of times, bouncing around like a pinball in a machine the size of a star. By the time it finally escapes from the surface, it has been transformed and scattered into something far gentler, the warm visible light that reaches your face on a sunny afternoon. That light you feel today left the core of the sun before modern humans existed. It survived 100,000 years of being bounced and absorbed and re-emitted before it finally crossed 93 million miles of empty space and landed on you. Energy that old. Energy that patient. Energy that crossed that distance at the fastest speed anything in the universe can move. And when it arrives, it is still the same total energy that was produced at the core. Nothing was lost. The accounting still balances. But now consider the carrier. Light itself, the thing that transported all that energy across all that distance, has a property that should be impossible by any normal physical logic. It has absolutely no mass. And that changes everything. A photon is a particle of light. It carries energy from one place to another. It travels from the surface of the sun to your face, from a light bulb to the wall behind it, from a distant galaxy to the eye of a telescope pointed at the night sky. And it weighs nothing. Zero mass. Completely in normal physics, energy and mass are tied together. Einstein's equation showed that mass is essentially stored energy, and anything with energy interacting with the world usually has mass to go along with it. Electrons have mass, protons have mass, neutrons have mass. Even neutrinos, which were long thought to be massless, turned out to carry a tiny amount of mass. Photons are the exception that should break the rule. They carry enormous amounts of energy across cosmic distances. A single high-energy gamma-ray photon carries enough energy to trigger a reaction in a detector the size of a building. And yet the photon itself has no mass whatsoever. How is that possible? How does something carry energy without having any mass? The answer comes from Einstein's full equation, not just the famous short version most people know. The complete version shows that massless particles can still carry energy through their momentum alone. A photon has momentum but no mass. Those two things can coexist in the mathematics, even if they cannot coexist in human intuition. And because photons have no mass, they are free to travel at the maximum speed the universe allows, the speed of light. That is not a coincidence. Massless particles must travel at that speed. It is a built-in rule of how space and time work. Anything with mass can approach the speed of light, but never reach it. Anything without mass can only travel at that speed, never slower. So the photon flying from the sun to your face has no choice. It travels at full speed, the only speed available to it, carrying its energy forward without any weight slowing it down. Here is the part that bends the brain. From the photon's perspective, if you could somehow ride along with it, no time passes at all. The moment the photon leaves the surface of the sun and the moment it arrives at your eye are the same moment from its frame of reference. The entire 8-minute journey that you experience watching the light cross from sunrise to your face is, for the photon, an event of zero duration. Time does not pass for a massless particle travelling at the speed of light. This comes directly from Einstein's theory of relativity. The faster you move through space, the slower time passes for you relative to stationary observers. At the speed of light, that slowdown is total. Time stops entirely. So the photon that hit your eye this morning left the sun and arrived in your eye in, from its own experience, the same instant. It never experienced the journey at all. It has always been here and always will have been there, simultaneously energy that travels at the fastest speed possible. Energy that has no mass, energy that exists in a state where time does not pass. And all of that is still simpler than what happens when there is no particle at all, when space itself, completely empty, holds energy. And that energy does something impossible. Take a box, remove all the air, remove all the particles, remove all the light, lower the temperature to absolute zero, the coldest possible state, where atoms stop vibrating entirely. Remove every single thing from that box until it is as empty as physics allows. Measure the energy inside. It is not zero. Empty space, the most perfectly empty space physics can create, still contains energy. A restless, churning, unpredictable energy that flickers in and out of existence at a scale so small it makes atoms look enormous. This is called the quantum vacuum. And it is one of the most verified and most baffling phenomena in modern physics. Here is why it happens. Quantum mechanics, the set of rules that governs the behavior of the very small, contains a principle discovered by Werner Heisenberg in 1927. The principle states that you cannot know both the exact position and the exact energy of a particle at the same time. The more precisely you measure one, the more uncertain the other becomes. This is called the uncertainty principle, and it is a fundamental feature of reality, not a measurement problem. That principle applies to empty space too. If a region of space had exactly zero energy, that would be a perfectly precise measurement. Zero, no uncertainty whatsoever. But quantum mechanics forbids perfectly precise measurements. so space cannot have exactly zero energy. The energy level of empty space must always fluctuate, rippling up and down around some minimum value that physics has not fully calculated. Those fluctuations are real. They produce real, measurable effects. One of the most famous is called the Casimir effect. Take two flat metal plates and place them extremely close together in a vacuum. The energy fluctuations of empty space push the plates together with a measurable force. Scientists have detected this force in laboratory experiments. It is small but real. Empty space is literally pushing objects around. Even more dramatic, quantum vacuum fluctuations can create actual particles. Pairs of particles appear spontaneously from the energy of empty space, one matter particle and one antimatter particle, existing for a fraction of an instant before they collide and annihilate each other, turning back into energy. These are called virtual particles, and they happen constantly, everywhere, in every region of space that exists. The energy that drives this process has no source, no fuel being burned, no reaction taking place. The energy of empty space is a baseline property of the universe, built into the fabric of reality at the most fundamental level. This matters for a reason that reaches far beyond laboratory curiosity. If empty space has energy, and the universe is mostly empty space, then the total energy stored in the vacuum of the cosmos is an almost incomprehensible number. Scientists tried to calculate it using quantum mechanics. Then they measured it by observing how the universe expands. The two numbers disagreed by a factor of 10 raised to the power of 120. That is the largest discrepancy between a theoretical prediction and a measured value in the entire history of science. By a margin so vast that calling it a discrepancy almost feels like an understatement. Something is very wrong with how physics understands the energy of empty space, and that something is connected to the biggest mystery in the entire universe, the force that is currently accelerating the expansion of everything. But before we get there, consider what happens when that vacuum energy shows up in the most violent flash of energy you have ever seen in a storm. A storm builds over your city. Clouds stack into a tower 15 miles high. Inside, ice crystals and water droplets collide billions of times per second, stripping electrons away from atoms and building up a massive electrical charge. The bottom of the cloud fills with negative charge. The ground below, covered in buildings and trees and wet asphalt, builds up a positive charge in response. The gap between the cloud and the ground becomes a wall of insulating air. For minutes the charge builds. The voltage difference climbs into the hundreds of millions of volts, and then the air itself breaks. A channel of ionized gas punches downward from the cloud toward the ground in a forking, branching leader stroke that moves at about 250 miles per second. The moment it connects with an upward-reaching discharge from the ground, the full stroke fires. Electrons rush downward through the completed channel. The whole event, from first leader to final strike, takes less than a second. In that fraction of a second, the air surrounding the lightning bolt heats to 50,000 degrees Fahrenheit. The surface of the sun reaches about 10,000 degrees Fahrenheit. A lightning bolt is 5 times hotter than the surface of the sun, for a moment so brief it barely registers as time. That temperature is so extreme the air around the bolt turns into plasma, the same state of matter that makes up the interior of stars. The plasma expands at supersonic speed, creating the pressure wave you hear as thunder. If you are close enough, the sound is less like a crack and more like a physical impact. All of that energy, that entire explosive release of heat and light and electromagnetic radiation, came from charge separation inside a cloud. From the mechanical energy of ice crystals bumping into each other millions of miles above your head, the average lightning bolt carries enough energy to power a 100-watt light bulb for about 3 months. That sounds useful. The problem is the timing. All of that energy releases in about a millisecond. There is no practical way to capture a millisecond of that power delivery and convert it into something usable. The grid cannot absorb it. The engineering challenge is enormous, so the energy flashes, lights up the sky, heats the air to star surface temperatures, and then it is gone, absorbed into the warming of the surrounding atmosphere as heat that spreads and dissipates and eventually becomes part of the background warmth of the planet. But the total energy of that bolt is still somewhere, still in the accounting system, still being tracked by the same universal ledger. It moved from charge in a cloud to heat in the air to microscopic vibrations in billions of gas molecules. Same total, different form. Now scale that up. If a lightning bolt strikes somewhere on Earth about 100 times every second, which it does, the energy output of Earth's storm system is staggering, and it is still nothing less than a rounding error compared to the energy stored in a different place, a place far quieter and far more dangerous. Inside your own body. Your body weighs somewhere between 100 and 200 pounds. Inside every pound of that, inside every atom, locked up in the relationship between protons and neutrons and the fields that hold everything together, sits a quantity of energy that almost nobody talks about. The total rest mass energy stored in an average adult human body comes out to roughly the equivalent of 30 large hydrogen bombs. 30 hydrogen bombs. Each hydrogen bomb in that comparison carries a destructive yield of around 1 megaton. The largest nuclear weapon ever detonated, the Soviet Tsar bomber tested in 1961, released about 50 megatons. So the energy sitting in your body, locked up in the mass of your atoms, exceeds that by many times over. None of it is accessible. The forces that bind atomic nuclei together are among the strongest in physics. Your body does not know how to perform matter-antimatter annihilation. Nuclear fusion requires temperatures found at the cores of stars. You are not in any danger, and neither is anyone near you. But the energy is real. Measurable, calculable, with simple arithmetic using Einstein's equation, mass times the speed of light squared. Plug in the weight of a human body, and the result is a number that belongs in a different conversation than biology. Here is what makes this stranger. The energy was always there. It was there when you were born. It is there right now, and most of it will still be there after you die. The atoms in your body will go on to become part of other things, trees, soil, air, eventually stars, and they will carry that energy forward intact. You are not generating that energy, you are borrowing the atoms that carry it for a few decades. The energy your body actually uses day to day, the kind measured in food calories, is a completely different category. The chemical energy in food is the energy stored in molecular bonds between atoms, not in the atoms themselves. When you eat and digest and move, you are tapping into bond energy, which is a tiny fraction of the total mass energy locked up in your matter. One food calorie, the kind printed on the back of a snack label, equals 4,184 joules of energy. Your body burns roughly 2,000 calories per day just to breathe and stay warm and pump blood. All of that is bond energy, chemical reactions, molecules breaking apart and recombining. The deep energy, the mass energy, stays untouched. Now put those two numbers next to each other. The energy your body uses in a lifetime of chemical metabolism is enormous by human standards, and it is still a tiny sliver of the total energy that simply exists in your matter, inert, waiting, locked behind forces that have never failed in the entire history of the universe. Your body is a slow, elegant machine, burning a small fire while sitting on a fuel source it will never ignite, and the organ that runs that machine, the one managing all those energy conversions, does it on a power budget that would embarrass a nightlight. Your brain weighs about 3 pounds. It makes up roughly 2% of your body's total weight. It uses about 20% of all the energy your body produces, and it does all of that on roughly 20 watts of power. That is less than the LED bulb probably lighting your room right now. A dim decorative bulb, a small candle equivalent electric glow. That is the power budget for the most complex object in the known universe. On 20 watts, your brain processes millions of incoming sensory signals every second. It filters almost all of them out before they reach conscious awareness. It coordinates the movement of every muscle in your body simultaneously. It maintains your sense of self, your memory, your language, your ability to imagine futures that have not happened yet. It does all of this continuously, even while you sleep, and it never asks you to think about it. For comparison, the human-designed computers that beat world champions at chess require tens of thousands of watts to operate. The massive data centers running the most advanced artificial intelligence systems on Earth consume megawatts, millions of watts, to process tasks that your brain handles with casual efficiency. The brain achieves this through a structure that has taken hundreds of millions of years of evolution to optimize. About 86 billion neurons, each one a biological cell that transmits electrical signals along thin fibers. Each neuron connects to thousands of others. The total number of connections in a single human brain exceeds the number of stars in the Milky Way galaxy. Each of those connections runs on electrochemical signals, ions moving across membranes, chemical messengers crossing tiny gaps. The energy cost of each individual signal is almost immeasurably small, but the efficiency of the system as a whole is something no human engineer has come close to replicating. Scientists who study the brain's energy use have calculated that the brain operates near the theoretical limit of computational efficiency, meaning it is not just impressive by biological standards, it is close to the maximum efficiency that the laws of physics allow for any information processing system. How evolution arrived at something close to the physical limit of efficiency without knowing physics is one of the genuinely open questions in neuroscience. Here is the uncomfortable implication. If the brain is running close to the physical limits of efficient energy use, and those limits are set by the laws of physics, then any mind anywhere in the universe that processes information and has developed over a long time would tend to converge toward the same energy efficiency. The laws of physics are the same everywhere. The pressure to be efficient is the same everywhere. That is speculation. Interesting, taken seriously by some researchers, but not proven. What is proven is the 20 watts. The constant quiet miracle of it. Right now, burning less power than a light bulb, your brain is holding this information, comparing it to things you already know, deciding whether it is interesting, and constructing the experience of listening to it. Energy flowing through biology so efficiently that science cannot yet explain the mechanism, and the efficiency goes even deeper than the brain, down to the atoms themselves, where something truly strange happens to the mass of a compressed spring. Pick up a spring, compress it, hold it tight. That spring now weighs more than it did before you compressed it. The difference is so small no scale on Earth could detect it. You would need equipment sensitive enough to measure individual atoms to have any hope of catching the change. But the increase in mass is real, and the reason it happens reveals something about the nature of matter and energy that most people never hear. When you compress a spring, you store potential energy inside it. You feel this as resistance, the spring pushing back against your hands, wanting to return to its original shape. That energy has to go somewhere while the spring is held compressed, and according to Einstein's equivalence between mass and energy stored in a system adds to the system's mass. This is a direct physical consequence of E equals mc squared, not a metaphor, not an approximation. The spring with stored potential energy is literally heavier than the same spring in its relaxed state, by exactly the amount its stored energy divided by the speed of light squared predicts. The same effect applies everywhere energy is stored. A charged battery weighs slightly more than a dead battery. A hot cup of coffee weighs slightly more than the same cup once the coffee cools. A compressed gas cylinder weighs slightly more than after the gas is released. The differences are so tiny they are essentially unmeasurable with ordinary tools. The change in mass from charging a phone battery is something like 1/1,000,000th of a gram, but the principle holds perfectly in every physics experiment that has ever been designed to test it. This has an implication that reaches far beyond springs and batteries. It means that mass is not a fixed, permanent property of matter. Mass changes based on how much energy a system contains. An object that gives off energy becomes lighter. An object that absorbs energy becomes heavier. The sun is the most dramatic example. Every second, the sun converts 4 million tons of its own mass into energy and radiates it outward in every direction. The sun is slowly losing mass. It is becoming lighter, very slightly, with every second that passes. Over its 4.5 billion year life, the sun has converted a significant fraction of its original mass into the light and heat that fill the solar system. Every photon of sunlight that ever reached Earth carried a tiny piece of what used to be the sun's mass, converted and sent outward as pure energy. And here is where that idea leads. If mass and energy are interchangeable, and if all the matter in the universe was once compressed into an incredibly hot, dense point at the start of the Big Bang, then at that moment the distinction between matter and energy may not have existed at all. Everything was energy. Everything, the matter you see today, the stars, the planets, every atom in your body, condensed out of pure energy as the universe cooled and expanded. You are not just powered by energy. You are made of energy that slowed down enough to hold a shape. That process, matter condensing from energy, happened in the first fractions of a second after everything began. And the man who first started to understand how heat connects to all of this was stirring water in a wooden barrel in 1843. The year was 1843. James Prescott Joule was 24 years old and running experiments in a room above his family's brewery in Manchester, England. He was not a university professor. He had no formal academic position. He was a brewer's son with a private income and an obsession with precision measurement. And he was about to prove something that most of the scientific establishment was not ready to accept. The dominant view at the time was that heat and mechanical work were completely separate things. Heat was thought to be a fluid, something called caloric, that flowed from hot objects to cold ones like water flows downhill. Motion was a separate phenomenon, governed by its own rules. The idea that heat and motion could be the same thing in different forms had been suggested before, but nobody had measured it precisely enough to make the scientific community pay attention. Joule built a device, a cylinder of water with a paddle wheel inside, connected by a string and pulley to a falling weight. When the weight dropped, it turned the paddle, which stirred the water. Joule measured the exact weight of the falling mass, the exact distance it fell, and the exact temperature increase of the water after the paddle turned. He found a precise, repeatable relationship. A specific amount of mechanical work always produced an exact, predictable amount of heat. Every time. Without exception. He repeated the experiment hundreds of times, with different amounts of water, with different weights, in different conditions. The relationship held every time. A fixed amount of mechanical work always converted into the same fixed amount of heat. This meant heat and work were not separate things. They were the same kind of thing, measured in different ways. Energy could move seamlessly between the form of motion and the form of heat, and the total amount stayed constant. Joule presented his results to the British Association for the Advancement of Science in 1843. The audience was polite but unimpressed. One member, a respected physicist named George Gabriel Stokes, made a few comments and the session moved on. The scientific community largely ignored the findings for several years. Eventually, after Joule published more careful experiments and other scientists began to take notice, the result became foundational. The first law of thermodynamics, the formal statement that energy cannot be created or destroyed, grew directly out of Joule's barrel of water. Today, the standard unit of energy in science is named after him. 1 joule is the energy required to lift a small apple about 1 foot off the ground. 1 food calorie equals 4,184 joules. Every energy calculation done anywhere in science uses the unit named after the man who stirred water in a brewery. The thing that Joule proved, that motion and heat are interchangeable forms of the same quantity, was the first real crack in the wall between different kinds of energy. Before Joule, heat was heat, and motion was motion, and light was light. After Joule, scientists began to understand that all of these were the same currency in different wallets. That idea has not stopped expanding since. and the next form of energy to fall under that umbrella is the one currently pulling every galaxy in the universe apart. In 1998, two separate teams of astronomers were doing the same thing, measuring how fast distant supernovae were moving away from Earth. A supernova is a star explosion so bright it can outshine an entire galaxy for a few weeks. Astronomers use specific types of supernovae as cosmic measuring sticks, because they always explode with roughly the same brightness. By measuring how dim one appears from Earth, scientists can calculate exactly how far away it is. Then they measure its speed. Then they can track how the expansion of the universe is changing over time. The expectation was clear. The universe has been expanding since the Big Bang. But gravity pulls everything together. Over billions of years, gravity should have been slowing that expansion down, the way throwing a ball into the air slows as gravity pulls it back. The supernovae should have confirmed that the expansion was decelerating. Both teams found the opposite. The expansion of the universe is speeding up. Galaxies are not just moving away from each other. They are moving away faster than they were 1 billion years ago. And faster than they were 2 billion years before that. Something is pushing space itself apart, overcoming gravity on cosmic scales, and accelerating. Whatever that something is, it is invisible. It does not interact with light in any way that detectors have ever measured. It does not clump together into clouds or planets or stars. It fills space uniformly, spread evenly through every cubic inch of the universe at the same density everywhere. Scientists called it dark energy, not because of any known property, but because it is dark in the sense of being unknown. The calculations of how much of it exists are staggering. Dark energy makes up roughly 68% of the total energy content of the universe. The normal matter, every star, planet, asteroid, gas cloud and living thing that has ever existed, makes up about 5%. Dark matter, another mysterious invisible substance that affects gravity, makes up the remaining 27%. 68% of everything that exists is something we cannot see, cannot detect directly, and cannot explain. The leading idea among physicists is that dark energy is the energy of empty space itself, the quantum vacuum energy discussed earlier. Empty space has a baseline energy level, and as the universe expands and creates more space, more of that baseline energy comes into existence, accelerating the expansion further. The problem is that when physicists calculate what that vacuum energy should be, using the best equations quantum mechanics and general relativity provide, the answer is wrong by a factor of 10 raised to the power of 120. The largest error in the history of scientific prediction. Something in the understanding of energy at the deepest level is deeply fundamentally off. The universe is being pushed apart by something that fills 68% of reality, and the best explanation physics can offer is mathematically impossible. And that gap between the energy we see and the energy we predict is exactly where the next discovery has to come from. The story does not get simpler from here, it gets stranger. A hurricane looks like weather. From space it looks like a spinning white disk, almost peaceful, organised into graceful spiral arms curling toward a clear eye at the centre. Inside that disk, the air is moving at over 100 miles per hour. The storm stretches 300 miles across. The clouds tower 10 miles into the sky, and the entire machine runs on one fuel source, warm ocean water. Here is the scale of what that fuel produces. A fully developed hurricane releases energy equivalent to a 10 megaton nuclear bomb exploding every 20 minutes. Around the clock. For days or weeks at a time, as long as the storm stays over warm water. A 10 megaton bomb every 20 minutes. That is 72 nuclear detonations per day, all of it coming from the evaporation and condensation of seawater. The mechanism is elegant in the way that terrifying things sometimes are. Warm ocean water evaporates into the air, carrying heat energy upward as water vapour. As that vapour rises and cools, it condenses back into water droplets, releasing that stored heat into the surrounding air. The released heat warms the air, making it rise faster, pulling in more warm, moist air from the ocean surface below. The rotation of the Earth causes the whole system to spin. A feedback loop builds, and the storm organizes itself into the structure you see from space. The ocean is the battery. The atmosphere is the engine. The hurricane is what happens when the battery has enough charge. Remove the warm ocean water, and the hurricane dies within days. This is why hurricanes always weaken rapidly after landfall. The fuel supply cuts off, and the machine begins winding down. Now consider the energy accounting. All of that explosive power, 72 nuclear bomb equivalents per day, comes from the sun heating the surface of the ocean over months. The sun deposited that energy into the water slowly, degree by degree, across an area millions of square miles wide. The hurricane releases it in concentrated form, quickly, violently, over a much smaller area. The energy was always there in the ocean. The hurricane is just a mechanism for moving it extremely fast into a different form. This pattern shows up everywhere in nature. Energy accumulates slowly and releases quickly. Tectonic plates grind for centuries and then snap in seconds, releasing stored energy as an earthquake. Charges build in storm clouds for hours and discharge in a millisecond as lightning. The slow accumulation and fast release is one of the most consistent patterns in how energy behaves. But none of those releases, not hurricanes, not earthquakes, not lightning, comes close to the efficiency of the most extreme energy conversion in physics. The one that turns matter completely and perfectly into light. When matter meets antimatter, both vanish. Every elementary particle has a corresponding antiparticle with the same mass but opposite charge. The antiparticle of an electron is called a positron. The antiparticle of a proton is an antiproton. When a particle and its antiparticle meet, they do not bounce off each other or stick together. They annihilate. Both particles cease to exist entirely, and their combined mass converts into pure energy in the form of gamma-ray photons at 100% efficiency. 100%. Every other energy conversion in physics is imperfect. A nuclear reactor converts less than 1% of its fuel into energy. A hydrogen bomb converts about half of 1%. The sun's fusion process converts less than 1%. Even the most efficient chemical reactions convert a tiny fraction of their mass into energy. Antimatter annihilation is the only process in known physics that achieves complete conversion. Zero waste. Zero leftover matter. The entire mass of both particles becomes energy. This is why antimatter is sometimes discussed in the context of future propulsion. A single pound of antimatter annihilating with a single pound of regular matter would release more energy than the largest nuclear weapon ever built by a factor of several hundred. A spacecraft powered by that reaction could potentially reach a significant fraction of the speed of light. The obstacle is production. Creating antimatter requires accelerating particles to near-light speeds and smashing them together in conditions that briefly recreate the energy densities of the early universe. The world's most powerful particle accelerator, the Large Hadron Collider near Geneva, Switzerland, produces a few trillion antiprotons per year. That sounds large until you realize that a trillion antiprotons have a combined mass of less than 1/billionth of a gram. Storing enough antimatter to fill a teaspoon, if it were ever produced, would require magnetic containment systems operating without interruption. Because the moment antimatter touches the container walls, it annihilates. The cost of producing 1 gram of antimatter using current technology has been estimated at tens of billions of dollars. And yet antimatter exists naturally. Cosmic rays striking the upper atmosphere create small amounts of it constantly. Certain radioactive decay processes produce positrons. The human body, due to the natural radioactive decay of potassium in your bones, produces a positron every few minutes. That positron annihilates with an electron almost immediately, releasing a brief flash of gamma radiation inside you. Right now, inside your body, matter and antimatter are meeting and vanishing, releasing energy, in a process so routine biology does not notice it. The universe does the same thing on a grand scale, and the energy released flows forward, unchanged, into the larger system. More fuel for the ledger that never loses a single entry. But where did all the matter in that ledger come from in the first place? And why is there any matter at all? The answer to that question connects to something so fundamental it changes the meaning of the word beginning. The universe started with a bang. That is the short version most people carry around. An explosion. A beginning. Something from nothing. The longer version is more unsettling. The Big Bang was the rapid expansion of space itself from an incredibly hot, dense state about 13.8 billion years ago. In the first fraction of a second, the temperature was so extreme that the distinction between matter and energy effectively did not exist. Everything was pure energy, packed into a space smaller than an atom. As space expanded and cooled, that energy began condensing into the first particles, then the first atoms, then eventually stars and galaxies and planets, and everything else. Here is the key part. The Big Bang did not create energy. The total energy of the universe did not start at zero and then get filled. What happened is that the energy which had always existed in that compressed state began expressing itself in new forms as conditions changed. Every star burning in the night sky is running on energy that has existed since before the universe had a shape recognizable to physics. Every particle of matter in your body is made of energy that predates the formation of galaxies by billions of years. The sun that warms you is converting energy that was present at the beginning of time into light, using a process that began 4.5 billion years ago. Nothing new entered the system. The energy was already there. This creates a question that physics currently cannot answer cleanly. If the total energy of the universe has always been the same since the Big Bang, what was the state of that energy before the Big Bang? What was it doing before space and time existed in recognizable forms? The word before is actually a problem here. Time itself began at or around the Big Bang. Asking what came before the Big Bang is a little like asking what is north of the North Pole. The question uses a concept, time, that may not apply to the situation being described. Some physicists propose that the universe has always existed in some form, cycling through expansions and contractions, with each Big Bang being a rebound from a previous collapse. Others propose that our universe emerged from quantum fluctuations in a pre-existing state, the way a bubble forms in boiling water. Others argue the question has no physical answer and falls outside the scope of science. All of those ideas are serious. All of them are incomplete. None of them has been proven. What all of them agree on is this: the energy in the universe today has not been added to or subtracted from since the beginning. Every unit of energy powering every process you have ever seen or touched or felt is part of the original supply. The supply that cannot be added to is also the supply that cannot be destroyed. That rule has never failed, and every time someone throughout history has tried to break it, they have failed. Every single time. Every crackpot inventor in history has tried, thousands of them. Across centuries, across every culture and country and era of human technology. Machines that spin forever without slowing down. Engines that produce more energy than they consume. Devices that draw power from nowhere. The dream of getting something for nothing has driven more failed engineering projects than probably any other idea in history. Every single one has failed, without exception. The concept they were trying to defeat is called conservation of energy, the first law of thermodynamics. The rule that energy cannot be created or destroyed, only converted from one form to another. The total in any isolated system stays fixed. The machines that tried to beat this law are called perpetual motion machines, and they fall into two categories. The first kind tries to produce motion that never stops, a wheel that keeps spinning indefinitely without any energy input. The second kind tries to produce more useful energy output than the energy put in, generating a surplus from nothing. Both are impossible, and the reasons are slightly different. The first kind fails because of friction. Every real physical system loses energy to heat through friction. Bearings, air resistance, internal material flexing. The losses may be tiny, but they are always present. A wheel spinning in what looks like a frictionless environment is still interacting with electromagnetic fields, still radiating a microscopic amount of heat, still losing something to the environment. The spin always slows. Always the second kind fails because of a deeper rule. Energy cannot be created. A system that outputs more energy than it receives would require energy to come from somewhere. If it does not come from a detectable fuel source, it must come from the internal structure of the machine itself. The machine would be consuming its own mass, like a star, and it would eventually run out. Patent offices around the world have formal policies rejecting perpetual motion machines without examination because the failure rate across history is 100%. No engineer is assigned to evaluate them. They go in a drawer. But here is the thing that makes this more than just a list of failed inventions. The unbroken record of conservation is itself a scientific result. Every failed attempt is another data point confirming the law. Every machine that slows down, every device that runs short, every budget that fails to balance is a vote for the same conclusion. The universe will not give you something for nothing, and the reason why Noether's theorem tells us is that time is consistent. The laws of physics tomorrow are the same as the laws today. As long as that is true, the books balance. But what if the books are hiding something? What if there is energy in the universe that the accounting system cannot reach? Energy stored so completely, so perfectly sealed away, that the normal rules of access do not apply? There is a place in the universe where that happens, where energy goes in and, by most calculations, never comes back out. And standing at the edge of that place, even imagining it, changes how you think about everything physics has told you so far. Sound is energy moving through air. When you speak, your vocal cords vibrate. Those vibrations push the air molecules around them, which push the next molecules, which push the next, in a wave of pressure changes travelling outward at about 760 miles per hour. When those waves reach someone's ear, they move the tiny bones inside, and the brain interprets the pattern as sound. Every decibel of that sound carries a measurable amount of energy, and that energy, like all energy, goes somewhere after the sound wave dissipates. It turns into heat. The slight friction of air molecules bumping against each other converts the sound wave's mechanical energy into a tiny increase in the temperature of the surrounding air. Now take that process and stretch it to an extreme. If a person yelled at maximum sustainable volume continuously without stopping for 8 years, 7 months and 6 days, the total sound energy produced would be just barely enough to heat 1 cup of coffee. 1 cup. 8 years. That comparison puts the scale of thermal energy into sharp focus. Heat is one of the most energy-dense things in everyday life, and sound is one of the least. The human voice, at full volume, produces roughly 1/1,000,000th of a watt of acoustic power. A cup of coffee requires around 350 joules of energy to heat from room temperature to drinking temperature. The math checks out, and the result is humbling. This also reveals something about how energy changes quality, not just form. Physics has a concept called entropy, which measures the disorder of a system. Heat is high entropy energy, spread out, diffuse, hard to concentrate back into anything useful. Sound and light are lower entropy forms of energy, organized, directional, easier to do work with. When energy converts from a lower entropy form to a higher entropy form, something is lost, not the energy itself. The energy is still there, perfectly accounted for, but its usefulness decreases. Heat spread evenly through a room cannot power a motor. Organized electricity can. The amount of energy did not change. The ability to do something with it did. This is the second law of thermodynamics. The total entropy of any closed system always increases over time. Energy flows from organized to disorganized, from concentrated to spread out, from useful to less useful, and that process cannot be fully reversed. The coffee cup yelling example is funny, the implication is enormous. Every energy conversion in the universe is trending in one direction, toward heat, toward disorder, toward a state where all the energy still exists but none of it can do anything. The universe is heading somewhere. The compass pointing the direction is entropy, and the destination, billions and billions of years away, is a place called the heat death. But before we get there, consider what happens to energy in the most extreme physical environment the universe can produce. A place where the accounting system breaks down completely. A professional pitcher stands on the mound and throws a fastball at 100 miles per hour. That ball has real kinetic energy. Kinetic energy is the energy of motion, and calculating it depends on two things: the mass of the moving object and the square of its speed. A 5-ounce baseball moving at 100 miles per hour carries about 140 joules of kinetic energy, enough to hurt badly if it hits you, enough to break glass, enough to be described in everyday language as fast and powerful. Now watch a garden snail crossing your driveway. It weighs about an ounce. It moves at about 0.03 of a mile per hour. Its kinetic energy is a number so small it is essentially unmeasurable in practical terms, essentially zero. But the snail's mass energy, the energy locked inside its matter following Einstein's equation, is incomparably larger than the baseball's kinetic energy. That 1-ounce snail contains enough mass energy to run every nuclear power plant on Earth simultaneously for several hours. The baseball, which is 5 times heavier, contains proportionally more. Both numbers dwarf the kinetic energy of the fastball by a factor so large the comparison becomes absurd. This is not a trick or a technicality. It is a fundamental feature of Einstein's equation. Mass energy scales with mass times the speed of light squared. Kinetic energy scales with mass times velocity squared. The speed of light is 186,000 miles per second. The fastball moves at 100 miles per hour, which is about a 27 millionths of a mile per second. The two numbers are in completely different categories. Light is about 7 million times faster than the fastball. Square that ratio and the difference in energy becomes incomprehensible. Everyday human experience with energy, throwing, running, burning fuel, is operating entirely in the kinetic and chemical energy range. Those numbers can be enormous by human standards. A rocket launch, a nuclear explosion, a hurricane, all of them still barely scratch the surface of the mass energy locked inside ordinary matter. This means the universe is far more energetic than it looks. Everything around you, every ordinary object, every person, every animal, every rock and drop of water and cubic foot of air is carrying orders of magnitude more energy than it will ever express through motion or heat or chemistry. The express energy is the iceberg's tip. The mass energy is everything underwater. And there are places in the universe where mass energy gets released on scales that redefine the word enormous, where entire stars collapse and the energy output in the first second exceeds what our sun will produce over its entire 10 billion year lifetime. But even that is not the most extreme thing energy does. There is one process that turns the energy dial as far as it goes: the collision that produces nothing but pure light. On a clear day, every square yard of ground facing the sun receives about 1,000 watts of solar energy. That sounds useful. The problem is that sunlight arrives as photons, particles of electromagnetic radiation, and extracting useful electrical power from them requires a conversion step that puzzled physicists for years. Here is what a solar panel actually does. The panel contains a thin layer of silicon, a semiconductor material. Photons from the sun strike silicon atoms in that layer. When a photon hits the right atom with enough energy, it knocks an electron loose from the atom. That loose electron can then flow through a circuit as electrical current. Gather enough of those electrons, and you have usable electricity. The process is called the photoelectric effect. Einstein did not win his Nobel Prize for relativity or for the famous equation. He won it in 1921 for explaining exactly this process. Before Einstein, scientists knew the photoelectric effect happened, but could not explain it using the prevailing theory of light, which treated light as a smooth, continuous wave. The wave theory predicted that the energy of ejected electrons should increase with the brightness of the light. Experiments showed that brightness made no difference. What determined the energy of ejected electrons was the colour of the light, meaning its frequency. Only the colour mattered. Einstein explained this by proposing that light came in discrete packets of energy, what we now call photons. Each photon carries a specific amount of energy determined by its frequency. A low-frequency photon carries too little energy to knock an electron free regardless of how many photons you shine. A high-frequency photon carries enough energy to do the job in a single hit. This was a revolutionary claim. It meant light was not just a wave, it was also a particle. The same beam of light had to be understood as both a wave that spreads through space and a stream of discrete particles that interact with matter one at a time. This dual nature is one of the most confirmed and most conceptually strange facts in all of physics. Experiments designed to detect waves always find waves. Experiments designed to detect particles always find particles. The same object. The same physical reality. Two completely different descriptions, both correct, neither one complete on its own. Solar panels convert roughly 15 to 22% of incoming solar energy into electricity under typical conditions. The rest becomes heat in the panel material. The conversion is genuinely remarkable, but the full theoretical limit of efficiency for a silicon solar cell, based on the physics of how photons interact with silicon's electronic structure, is about 33%. Researchers have built multi-layer cells that exceed this by stacking different materials, each one optimized for a different part of the solar spectrum. Laboratory cells have exceeded 40% efficiency. Commercial deployment of those cells remains expensive, but the fundamental limit comes from the nature of energy itself. Photons above a certain energy level waste their excess energy as heat when they knock electrons free. Photons below the threshold do not contribute at all. The physics of the transaction is locked in, and no engineering solution changes the underlying rules. Energy flowing from the sun to your phone battery passes through at least 3 conversions on that journey. Each one is governed by rules that nobody designed and nobody fully understands at the deepest level. The rules just are. And every machine we build, every panel and wire and circuit, is a way of navigating within them. The direction those rules point over long enough timescales is always the same. Toward disorder. Toward evenness. Toward stillness. The second law of thermodynamics has a direction. Heat flows from hot to cold. Energy spreads from concentrated to diffuse. Order breaks down into disorder. These are not tendencies or approximations. They are reliable enough that engineers stake their lives on them every day. A cup of hot coffee left on a table will always cool toward room temperature. The room will warm by an imperceptible amount. The two temperatures will creep toward each other. Eventually, if you waited long enough in a perfectly sealed room, the coffee and the air and the table and everything in the room would reach exactly the same temperature. Perfectly uniform. No gradients, no flow of energy possible in any direction. That final state is called thermal equilibrium. And when it is reached, nothing can happen. No heat can flow because there is nowhere for it to go. No work can be done because work requires an energy difference, a potential, a hill for energy to roll down. Everything just sits at the same temperature forever. Now scale that up to the universe. The universe contains enormous energy gradients right now. Stars are billions of degrees hotter than the space around them. Black holes sit at nearly absolute zero, while the matter falling into them reaches temperatures of trillions of degrees. Galaxies rotate. Supernovae explode. Energy flows constantly from hot regions to cold ones. But those gradients are temporary. Stars burn out. The energy they release spreads into the surrounding cosmos, warming it by unmeasurable amounts. Over time, the hot spots cool and the cold spots warm, very slightly, very slowly. The gradients flatten. In roughly 100 trillion years, the last small stars will exhaust their fuel and go dark. The universe will be cold, dark, and filled with the dead remnants of stars. For a time, black holes will remain, the last concentrated sources of significant energy. Over timescales that make 100 trillion years look brief, those black holes will slowly evaporate through a process called Hawking radiation, converting their mass into a thin trickle of low-energy photons that spread into space. Eventually, no temperature differences will remain anywhere in the universe, no energy gradient of any kind. Every particle will sit at the same tiny fraction above absolute zero, separated by vast distances, with no reactional process possible between them. The total energy of the universe will be exactly the same as it has always been, perfectly conserved. But utterly useless, spread so evenly across such an enormous volume that nothing, anywhere, can do anything with it. Physicists call this state the heat death of the universe. Maximum entropy. The end of all processes. The energy does not disappear. It never disappears. It just spreads out until it can never be gathered back. The universe runs down, not because it runs out of energy, but because the energy loses all structure, all difference, all potential. Everything that has ever happened, every star and planet and organism and thought, was a temporary eddy in that flow, a brief moment where energy moved from one form to another before continuing its journey toward evenness. But before that final stillness arrives, there is a place in the universe where energy vanishes from reach so completely it changes what the word accessible means. A black hole forms when a massive star collapses under its own gravity at the end of its life. The core, left unsupported after the outer layers explode away in a supernova, crushes down into a point of infinite density. The gravity around that point becomes so strong that the escape velocity, the speed needed to pull away from it, exceeds the speed of light. Since nothing in the universe moves faster than light, nothing can escape. Light itself, travelling at 186,000 miles per second, cannot pull away from the gravitational well past a certain boundary called the event horizon. Everything that crosses the event horizon is permanently inaccessible from the outside universe. Now here is the energy question. When matter falls into a black hole, what happens to its energy? The total energy of the universe must remain constant. Conservation of energy cannot be violated. So the energy has to go somewhere. From the outside, the answer is that the energy becomes part of the black hole's total mass energy. A black hole that swallows a star becomes slightly more massive, its gravity slightly stronger, its event horizon slightly larger. The energy is still in the universe. It is still being counted in the cosmic ledger. It just cannot be accessed from outside the event horizon. This is a different kind of conservation. The energy exists. It is locked away completely. The accounting balances, but the balance is held inside a sealed vault with no door. For most of the 20th century, physicists thought black holes were permanent. Energy went in and stayed in forever. The mass of a black hole would only ever increase as it swallowed more matter. Then in 1974, Stephen Hawking used a combination of quantum mechanics and general relativity to predict something that changed that picture entirely. Black holes are not perfectly sealed. The quantum vacuum, that boiling sea of energy and empty space that creates virtual particle pairs constantly, behaves differently near an event horizon. Pairs of virtual particles appear near the edge. One particle falls across the horizon into the black hole, the other escapes into space. To an outside observer, energy appears to radiate away from the black hole, very slowly, incredibly slowly for large black holes, but steadily. This is called Hawking radiation. It means black holes have a temperature. They are technically warm objects, though for a black hole the mass of a star, the temperature is a fraction of a millionth of a degree above absolute zero. Over incomprehensibly long timescales, a black hole will radiate all its mass energy away as Hawking radiation, shrink steadily, and eventually evaporate completely in a final burst of energy. The energy that fell into the black hole comes back out, eventually in a form so scrambled, so spread across all frequencies of radiation, that recovering any useful information from it may be physically impossible. The energy returns. The information about what fell in may be gone forever. Whether information is truly destroyed in this process is one of the most hotly debated questions in theoretical physics, known as the black hole information paradox, and it remains unsolved. Energy obeys the conservation law, but the conservation law, it turns out, says nothing about what form the energy takes when it returns, and the form it returns in matters enormously to what comes next in the universe's story. Stephen Hawking published his prediction about black hole radiation in 1974. He was 32 years old and had already been living with a motor neuron disease for over a decade, a disease that would eventually leave him completely paralyzed. He did his most important theoretical work during years when his physical condition was rapidly deteriorating. The prediction was unwelcome. Hawking's colleagues initially pushed back. The idea that black holes radiated energy seemed to contradict a recently proven theorem about black holes, one that said the total event horizon area of all black holes combined could never decrease. If a black hole radiated energy and lost mass, its horizon area would shrink, violating the theorem. Hawking's response was that the theorem was a classical result, meaning it applied to smooth, large-scale physics. Quantum mechanics operated by different rules at small scales, and at the boundary of a black hole, quantum mechanics could not be ignored. He was right. The evaporation process he described followed conservation of energy. The total area theorem remained valid for the combined system of the black hole plus the radiation it emitted. The contradiction dissolved when the full picture was considered. The mechanism itself comes directly from the quantum vacuum behavior described earlier. Empty space constantly produces pairs of virtual particles, a particle and its antiparticle, that appear and annihilate each other almost instantly. Near an event horizon, the geometry of space-time separates some of these pairs before they can recombine. One member of the pair falls inward past the horizon. The other escapes outward. From outside the black hole, it appears as real radiation coming from the vicinity of the event horizon. The energy for that escaping particle comes from the black hole itself. The infalling particle carries negative energy from the perspective of a distant observer, effectively reducing the total mass energy of the black hole by the same amount the escaping particle carries away. The books balance. The energy is conserved. The black hole slowly loses mass. For a black hole the size of the Sun, the temperature of Hawking radiation is so low that the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, is far hotter. The black hole is actually absorbing more energy from the background than it radiates. Such a black hole would grow, not shrink, only when the universe cools below the temperature of a given black hole's Hawking radiation will that black hole begin to lose more than it gains. For stellar mass black holes, that point is so far in the future that the numbers lose meaning in human terms. But Hawking radiation carries a deeper problem that physicists have argued about for decades. When the black hole finally evaporates, where did all the information about what fell in go? The matter and energy that crossed the horizon carried detailed information, the specific quantum states of every particle, every arrangement of every atom. Hawking radiation appears to be completely random, carrying no record of what produced it. If that is true, information is destroyed, and destroying information may be equivalent to violating the laws of quantum mechanics, which say information is always preserved. This paradox has driven some of the most intense theoretical physics of the past 50 years. Many of the best minds in physics have taken strong positions on it. No consensus has emerged. The question of what happens to energy and information at the absolute extreme edge of physical reality remains genuinely open, which makes what happens at the smallest possible scale of energy equally provocative. Cool a gas down, the molecules slow. Cool it further, and they slow more. Keep cooling toward absolute zero, the temperature at which all thermal motion should stop. And at some point the gas becomes a liquid, then a solid, then the atoms should cease vibrating entirely, except they never do. Even at absolute zero, particles continue to move. They have a baseline energy that cannot be removed no matter how cold the environment gets. This is called zero-point energy, and it is one of the most verified predictions of quantum mechanics. The reason goes back to Heisenberg's uncertainty principle. To have zero kinetic energy, a particle would need to be perfectly at rest, with a precisely known momentum of zero. But the uncertainty principle forbids perfectly known momenta. If momentum is precisely zero, the uncertainty principle demands that the particle's position becomes completely unknown. The particle cannot have both a definite position in space and zero energy simultaneously. One or the other must carry uncertainty. So every particle in the universe has a floor, a minimum energy level it can never drop below. Even at the coldest temperature physically achievable, the particles in a material retain this baseline energy and continue to vibrate. This is not a theoretical abstraction. Engineers who build quantum computers and ultra-precise sensors must account for zero-point energy fluctuations. They create real noise in sensitive measurements. They set real limits on what any detection technology can achieve. The most dramatic demonstration of zero-point energy at the material scale came with the discovery of superfluidity. Liquid helium, cooled to within a fraction of a degree above absolute zero, behaves in ways that defy ordinary physics. It flows without friction through pipes. It climbs up and over the walls of its container. It has zero viscosity, meaning nothing slows it down internally. This happens because at those temperatures, quantum effects take over the entire fluid, and the zero-point motion of the atoms prevents them from ever freezing into a solid crystal, even with no heat energy at all. Helium remains liquid all the way to absolute zero at normal pressure, purely because of zero-point energy. Every other element on Earth solidifies before reaching that temperature. Helium refuses because the quantum uncertainty of its atoms keeps them in constant motion even when all heat has been removed. Now extend that idea outward. Every field in the universe, the electromagnetic field, the gravitational field, every quantum field that makes up the fabric of physical reality, has a zero-point energy. The vacuum of space is filled with the zero-point fluctuations of every field simultaneously. This is what produces the quantum vacuum energy discussed earlier, and it is the source of the colossal disagreement between theoretical prediction and observation that keeps physicists awake. Absolute zero is not the bottom of reality, it is the bottom of temperature. Below temperature, there is still energy. The universe hums at a level that nothing can silence, and that hum, that baseline vibration of every field in existence, may be the key to the single most important unsolved problem in cosmology. Because one of those fields, the one responsible for dark energy, may be doing something unexpected, something that changes the story of how the universe ends. When astronomers measured the acceleration of the universe's expansion using distant supernovae in 1998, the simplest explanation was a constant, a fixed energy density for empty space that stayed the same everywhere and at all times. Einstein had actually included something like this in his equations decades earlier, calling it the cosmological constant, a term he later said was his greatest blunder. The 1998 discovery suggested it was not a blunder at all. But constant is a very specific word, and in physics, constants have a way of turning out to be variables. In 2024, a massive survey called the Dark Energy Spectroscopic Instrument released results from mapping the three-dimensional positions of tens of millions of galaxies across more than a third of the visible universe. The survey measured how the expansion rate of the universe changed over the last 11 billion years, building the most detailed picture ever assembled of cosmic expansion history. The data suggested something unexpected. Dark energy may have been stronger in the past and may be weakening now. The expansion of the universe may not be accelerating at a constant rate. The energy density of empty space may be evolving over time. If that is confirmed by future observations, it overturns the simplest version of the story entirely. A changing dark energy means the fate of the universe is different from what the standard model predicts. If dark energy weakens enough, the expansion of the universe could slow, stop, and reverse. Galaxies would begin moving toward each other instead of apart. Eventually, everything would collapse back into an incomprehensibly hot, dense state. A big crunch. Alternatively, if dark energy strengthens instead of weakening, the expansion could accelerate without limit. Galaxies would eventually move apart faster than light can cross between them. Then, galaxy clusters. Then, individual galaxies would be torn apart. Then, solar systems. Then, planets and stars and eventually atoms themselves would be ripped apart by the accelerating expansion of space. This is called the Big Rip. The 2024 data is not conclusive. It is one data set, and it needs to be confirmed by other instruments and other methods. The error bars are large enough that the standard constant dark energy is still within the range of possibilities. But the fact that it is no longer the only possibility makes this one of the most active areas of physics right now. Because the energy that makes up 68% of the universe, the energy nobody can see or touch or detect, the energy whose origin nobody understands, may be changing, and if it is changing, the question of what it is becomes even more urgent. A changing energy density of empty space over time would have implications for Noether's theorem. If the laws governing dark energy are evolving, then the system they govern is not perfectly time-symmetric. And if time symmetry breaks, conservation laws bend, the universe may be playing by slightly different rules today than it was 10 billion years ago. And nobody has the equation that describes how the rules are changing. Your brain is processing these words right now. Neurons are firing. Electrical signals are crossing synaptic gaps. Proteins are being produced. Blood is flowing. Oxygen is being consumed. All of that is energy converting from one form to another, moment to moment, in a pattern so specific and so organized that the result is the experience of understanding language. The question nobody has answered is whether the experience itself is the energy process, or something else entirely. This is called the hard problem of consciousness, and it has been discussed seriously by physicists, neuroscientists, and philosophers for decades. The easy problem, and it is only easy relative to the hard one, is explaining what the brain physically does when it perceives, thinks, and remembers. Scientists have made enormous progress on that. They can map which brain regions activate during different experiences. They can trace the electrical patterns associated with specific thoughts. They can measure the energy usage of consciousness down to individual neurons. The hard problem is explaining why any of that physical process produces subjective experience at all. Why does the firing of specific neurons feel like anything from the inside? Some researchers have tried to connect consciousness to quantum mechanics and energy at the most fundamental level. In the 1990s, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that consciousness arises from quantum processes in structures inside neurons called microtubules. These structures, they argued, might perform quantum computations that collapse in a way that produces conscious experience. The idea remains extremely controversial and lacks experimental support, but it has never been definitively ruled out. What is less controversial is the energy efficiency argument. The brain operates at roughly 20 watts, and some calculations suggest it runs close to the theoretical limit of efficient information processing for any physical system operating under the laws of thermodynamics. If consciousness requires a physical process, and physical processes have efficiency limits, then there may be a minimum energy cost for any conscious experience. That would mean consciousness is not just powered by energy. Consciousness would be bounded by energy, limited by it, shaped by it in the same way every other physical process is shaped by thermodynamics. Whether that insight brings us closer to understanding what consciousness actually is remains an open question. The equations describe what the brain does with energy. The experience of being inside that process is not captured by any equation yet written. And if energy itself is ultimately a mathematical property with no physical substance underneath, then everything that runs on energy, including consciousness, including the experience of listening to these words right now, may be grounded in something that no physical object has ever touched. That is not a comfortable place to stop. It is, however, exactly where the next question begins. Energy has no substance. It is a mathematical property, a number that systems carry, a quantity that stays constant across transformations. Matter is energy in a different form. Fields are mathematical descriptions of how energy is distributed through space. The particles those fields describe are excitations, ripples in an underlying mathematical structure. Follow any physical object all the way down to its smallest components and you reach, at every level, equations, relationships, numbers. At some point, a reasonable person has to ask, is there anything underneath the math? This is called the philosophy of physics, and it is taken seriously by people who normally never bother with philosophy. When physicists like Max Tegmark at the Massachusetts Institute of Technology argue that the universe is literally a mathematical structure, they are making a claim that would have seemed absurd to scientists a century ago. The argument goes like this: the universe behaves exactly as if it were described by mathematics, because it is mathematics. Physical reality and mathematical structure are the same thing. If that is true, if the universe is made of math rather than of some underlying physical stuff that math merely describes, then energy is not a property that something physical carries. Energy is the math itself. The equations do not represent reality. They are reality. This idea connects directly to the simulation hypothesis, the proposal that the universe may be a computational process running inside a more fundamental system of some kind. Physicists and technologists, including Elon Musk and theoretical physicists like James Gates, have discussed this seriously, though the idea falls outside the range of testable science as currently understood. The connection to energy is straightforward. In a computational system, information processing requires energy. Real computers running on real chips consume real electricity. If the universe is computational, then the energy within it might be equivalent to the processing power of whatever is running the simulation. The laws of conservation of energy would be conservation of computational resources. The limits of physics would be the limits of the simulation's capacity. Nobody knows how to test this. There is no known observation that could distinguish between a real universe and a perfectly simulated one. That may be a fundamental limit, or it may be a challenge waiting for a future physicist to solve. What makes this more than idle speculation is where it sits in the broader picture. Science has discovered, layer by layer, that physical reality is progressively less physical than it looks. Solid matter is mostly empty space. Particles are probability waves. Mass is frozen energy. Energy is a conserved number with no physical location. Every layer of analysis finds something more abstract underneath. The direction of that progression is consistent and clear. At the end of it, the question that Feynman could not answer in 1961 may not be answerable by looking for a physical thing called energy, because energy may be the most fundamental thing that exists, and asking what it is made of may be like asking what existence is made of. The man who understood that better than almost anyone else spent the last 30 years of his life trying to prove that all the energy in the universe was one thing in disguise. He did not succeed. But the failure itself points somewhere important. Albert Einstein published his theory of special relativity in 1905. He published general relativity in 1915. By then he had already done more to reshape physics than almost any scientist before him. He was 46 years old and at the height of his reputation. He spent the next 30 years working on a single problem and never solved it. The problem was unification. Einstein wanted to show that all the fundamental forces of nature, gravity, electromagnetism, and the forces inside atomic nuclei were different expressions of a single underlying field. One mathematical structure that explained everything. One kind of energy in different costumes. He called this work the unified field theory. He worked on it obsessively, filling notebooks with equations, publishing drafts, withdrawing them, starting over. He largely withdrew from the mainstream of physics during those decades, which had moved on to quantum mechanics, a field he deeply distrusted because of its fundamental randomness. He believed the universe operated deterministically, that God, as he put it, did not play dice. The rest of physics left him behind in some ways during those years. Quantum mechanics produced extraordinary results. Weapons and transistors and lasers, all built on principles Einstein found philosophically unacceptable. He continued working on unification alone. He never finished. At the time of his death in 1955, his final papers were on his hospital bed. He had been working on the unified field theory until his last days. His latest attempt was as incomplete as all the previous ones. What Einstein was reaching for has not been achieved in the 70 years since. Physicists today call the same problem the theory of everything, and the leading candidate is string theory, which proposes that all particles and forces are different vibration modes of tiny one-dimensional strings of energy. String theory requires 10 or 11 dimensions of space, most of them too small to detect with any instrument. It makes predictions that have not been verified experimentally. It remains mathematically beautiful and physically unconfirmed after decades of work by thousands of researchers. The other main approach, called loop quantum gravity, attempts to quantize space and time themselves, treating the geometry of reality as made up of discrete units rather than a continuous smooth background. It has its own deep problems. Neither theory has succeeded in unifying all forces. Neither has connected quantum mechanics to gravity in a way everyone accepts. The two great frameworks of modern physics, quantum mechanics governing the very small and general relativity governing the very large, remain mathematically incompatible. They produce contradictory predictions at the scales where both should apply simultaneously. Einstein's dream of one energy, one field, one underlying structure remains unrealized. The equations we have describe reality with extraordinary precision within their domains. Outside those domains, at the places where they overlap, the math breaks down. And in those places, where the two great theories of reality collide and contradict each other, the nature of energy becomes most unclear, which brings everything back to the question that started it all. The question Feynman asked his class to sit with in 1961. The question that 300 years of science has circled without ever landing on an answer. Here is everything physics knows about energy. Energy is conserved. In every experiment ever conducted, across every scale from subatomic particles to galaxy clusters, the total energy of a closed system stays constant. No exception has ever been recorded, no machine has ever cheated it. No natural process has ever produced or destroyed a single unit. Energy transforms. It moves between forms without losing any of its total quantity. Heat becomes motion. Motion becomes electricity. Electricity becomes light. Light becomes chemical energy. Each conversion follows precise rules. The accounting always balances. Energy and mass are the same thing. Every gram of matter in the universe holds a staggering amount of energy, related by the speed of light squared. Matter is energy that has taken a stable, concentrated form. empty space is energy in its lowest, most diffuse state. The universe, from its densest black holes to its emptiest voids, is saturated with energy in different expressions. Energy conservation is tied to time. Emmy Noether proved that as long as the laws of physics remain consistent from one moment to the next, energy will remain constant. Time and energy are bound together in a relationship that goes all the way down to the mathematical structure of reality. And yet, nobody knows what energy is. Feynman said it in 1961. Every physicist who has looked at the problem deeply has arrived at the same boundary. The equations are perfect. The predictions are exact. The rule is unbroken. And the thing the equations describe, the actual nature of the conserved quantity, the reason this number exists and stays constant and runs everything from heartbeats to supernovae, remains completely unknown. This is not a small gap waiting to be filled by the next research paper. It is a foundational blank space in human understanding. The most important concept in all of science, the thing everything else is built on, is something nobody has ever defined without eventually going in a circle. The closest thing to an answer that physics has produced is this: energy may be a property that reality has, the same way a triangle has angles. Asking what energy is made of may be like asking what the angles of a triangle are made of. Angles are not made of anything. They are a relationship between lines. Energy may be a relationship between states of the universe, a measure of how much change is possible from any given configuration. If that is true, then energy is not a thing. It is a measure of things, a way the universe keeps track of its own capacity for change. Every star burning, every neuron firing, every photon racing between galaxies, every quantum fluctuation in empty space, all of it is the universe expressing its capacity for change. In every form available, at every scale, in every corner of the cosmos. And that capacity, that restless, unstoppable, constantly shifting potential for change, has been running since before time had a recognizable shape. It will keep running until the last gradient flattens and the last energy difference in the universe equalizes and the cosmos settles into the final, perfect, permanent stillness of maximum entropy. The question of what energy is will probably outlast every star currently burning. It might be the last question physics ever answers, or it might be the question that forces physics to become something entirely different from what it is today.